Three scientists, two from USA and one from Japan, they synthesized a compound, polymer, that conduct the electricity. They reported this polymer first. That is a polymer made from the acetylene gas. So when they started the reaction acetylene, they got two products, cis polyacetylene and trans polyacetylene. Okay, we'll study this in this topic. The scientist names are Alan Giger, Alan McDermott, and Hideki Shirakawa. Hideki Shirakawa professor is from Japan, and the other two professors are from USA. They have changed the view with their discovery that a polymer, that is polyacetylene, can be made conductive almost like a metal. Discovery of conducting polymers, the introduction part. Discovery in the late 70s, 1977, by Alan Giger, Hideki Shirakawa, and Alan McDermott. Before, the polymers were used as insulators in the electronic industry. Advantages over conductors: chemical ion transport possible, redox behavior, catalytic behavior, electrochemical efforts, photoactivity, junction effects. Mechanical, lightweight, flexible, non-metallic surface properties. Conducting polymers. Those polymers which conduct the electricity are called conducting polymers. The conduction of polymer may be due to the unsaturation or due to the presence of externally added ingredients in them. The conducting polymers can be classified in two ways. One is intrinsic conducting polymers, other one is extrinsic conducting polymers. Intrinsic polymer with conjugation, doped conducting polymers. On the other hand, extrinsic conducting polymers can be subclassified as conductivity element and blended conducting polymers. Conductivity. Polymers become conducting upon doping. Polymers becomes electronically charged. Polymer chains generate charge carriers. Concentration of dopant causes certain electrons to become unpaired. Formation of polarons and bipolarons takes place in the reaction. They have extended by p orbital systems. Doping in polyacetylene. Amount of dopant used is significantly higher. So doped polyacetylene is always in trans form. It is a trans form, TRANS form. Neutral polyacetylene can be doped in two ways. P-doping means oxidation with anions, that is a perchlorate. This is trans polyacetylene. So a doping means oxidation with anions. That means we have to remove one electron from this polymer. That means only after the removal of one electron, this will be formed a cationic species. So in the presence of a perchlorate anion, N-type doping, reduction with cations, that is Na+. Here we add the electron, it forms carbanion. There we remove the electron, that is carbocation. In the second case, we use Na+. Reduction with Na cations, there it is oxidation with anions. Method of doping, chemical oxidants. Okay, iodine, nitronium species, transition metal salts. Chemical reducing agents, sodium naphthalate, electrochemical methods, perchlorate, PF4 anion, and other complex species. So chemical oxidants, chemical reducing agents, electrochemical methods, three methods by which we do the doping process. Doping with iodine. This is acetylene or ethane. Okay. So this is converted into polyacetylene. That is a polymerization. Like ethylene, polyacetylene. There are also acetylene and polyacetylene. There are two possibilities. One will be cis form, one will be trans form. Here it is in trans form. You can see that here there is a double bond and single bond and double bond. So this, if you see, it is trans form. Okay. This is polyethylene or polyacetylene. There are chances that there is a chances of a double bond migration from one place to other place. Okay. And if you add iodine into it, so what iodine will do? Iodine will act as oxidizing agent. It will oxidize this polymer with the formation of carbocation over the carbon, and it forms I3 minus, iodate minus. So due to this oxidation, there is a vacancy in the plus charge. There is a vacancy in the polymer chain. The effect of dopants, conductivity increases upon up to a certain doping level, stability decreases, morphology due to the presence of charges, shape will not be retained, reason why doped polyacetylene is always trans. Plot of conductivity versus the doping. So doping level in conductivity. So at 0.1, there is a sudden rise in the conductivity. Okay, it's around from 100 to 200, and at 0.2 it is getting saturated. This line is a saturation point. Challenges, reproducibility, stability of the material, difficulty to process, short lifespan, high cost, difficult to fabricate in laboratory. These are all the challenges in the conducting polymers. Okay. Types of conducting polymers: aromatic cycles, double bonds, no heteroatom, nitrogen containing heteroatom, sulfur containing heteroatom. So polyfluorines, polyphenylines, polypyrenes, polyazulines, polynaphthalines. Nitrogen containing means polypyrrole, polycarbazole, polyindole, polyazabines, polyaniline. Sulfur containing means polythiophene, and then poly 3,4 ethylene dioxythiophene, polyphenyl sulfide. Double bonds, polyacetylenes, PAC. Aromatic cycles and double bonds, polyphenylene, vinylene. Types of doping agents: neutral dopants, ionic dopants, organic dopants. These are all three types of dopants, and polymeric dopants. The neutral dopants, the best example is iodine. Iodine is the best oxidant. And also besides iodine, we have bromine and arsenic fluoride, sodium, potassium, sulfuric acid, perchloride. Ionic dopants: lithium perchlorate, iron perchlorate, trifluoromethyl sodium trifluoromethyl sulfonates, tertiary butyl uh, perchlorate. These are all examples for ionic dopants. Organic dopants, trifluoroacetic acid, trifluorosulfonic acid, sodium salt, para-toluene sulfonic acids. Polymeric dopants, PVS and PPS. Applications. Conducting polymers have many uses. The most documented are as follows. Anti-static substances for photographic film, corrosion inhibitors, compact capacitors, anti-static coating, electromagnetic shielding for computers, smart windows. The second generation of conducting polymers have been developed. These have industrial uses like transistors, light-emitting diodes, lasers used in flat televisions, solar cells, displays in mobile telephones, and mini-format television screens. These are all some of the images of conducting polymers. Shield for computer screen against electromagnetic smart windows radiation, photographic film, solar cell, smart windows, light emitting diodes. So they have received the Nobel Prize in the year 2000 for this conducting polymer discovery. Mechanism of conductance. So the band gap plays a major role in planning for a polymer synthesis. So we know that in metals, mainly copper, the band gap between valence bond and conduction band is almost zero. This is the band gap. Whereas in insulators, the band gap is very, very high, the gap. So the jumping of electrons from here to here will be very challenging. In semiconductors, it's not that much larger in gap. So silicon, germanium, these are all semiconductors. This valence bond, this is conduction bond. So the electrical conduction could occur only after thermal or photolytic activation of electrons to give them sufficient energy to jump the gap and reach into the lower levels of the conduction band. Examples are this. These are the structures, and this is the band gap. This is the conductivity. Conductivity unit is Siemens per centimeter. This is electron volt band gap. Structures, and here the highest band gap is 3.2, that is for polyaniline, and lowest band gap is 1.5, that's for the polyacetylene. So this is the conductivity, 10 to the power 3 to 1.7, 10 to the power 5 is the highest conductivity. Lowest conductivity is that has higher band gap, that is this one 3.2, that is 30 to 200 Siemens per centimeter. So the conducting mechanism in polyacetylene. So unsaturated polymers consist of hydrogen and sp2 hybridized carbon atoms, sigma and bibonds of a polycarbon-carbon backbone. The localized electrons from the backbone of polymer chain and dominate the mechanical properties. The electrons in the bibond are delocalized along the chain and are responsible for optical and electrical properties of conducting polymers. So conduction mechanism in polyacetylene, the current along the polymer chains can only flow if one or more electrons are removed or added to it. It's the polymer, so iron is treated into that. So the carbon is getting a positive charge and the iodine will convert into iodate. So the positive charge will act as a charge carrier for conducting the electrons. This you can see here. There is a positive charge here. So because of the positive charge, the double bond will migrate here. Okay. So there's a formation of iodate and charge carrier. See, there is a delocalization of the bibonds. So the polymer, upon oxidation with iodine, we end up with oxidized species. It is P doping. That means it is a doping process that will give us a positive charge. Other one is N doping. Okay, that we add some reagents that will give us a negative charge over the polymer and positive charge of the sodium metal ion. The lone electron of pi bond from which an electron was removed can move easily. Due to this, the double bond successfully moves along the chain. This is a pictorial diagram of conducting polymers, where if you see carefully here, copper is placed at the top, 10 to the power 6 conductivity units. And until now, copper is the best conducting metal. So these polymers are, you can see here, the polymers reached up to here. Polypyrrole is somewhat here. Just put a line here. Polypyrrole reached 10 to the power 3, almost somewhere here. Okay, the other polymers, polyphenol sulfide, polyphenylene, polyacetylene, polyaniline, polythiophene are below the polypyrroles. The unit is Siemens per centimeter. Contrast between isomers of polyacetylene, isomers cis and trans, conductivity 10 to the power minus 13, 10 to the power minus 7. Obtainable temperature minus 77 degrees Celsius. This is 170 degrees Celsius. This is cis isomer. This is trans isomer. In batteries also, these conducting polymers are greatly used because of its speciality of lightweight, rechargeable behavior. Examples: polypyrrole, lithium and polyaniline materials. Here you can see that. So there's a valence band and conduction band. There is a gap. When the polymer is getting oxidized, we have a positive charge generated in the linear chain. And neutral, this is a radical species generated at the carbon atom. This is negatively charged solution generated over the carbon atom. So you can see the different category. So one radical means one electrons are placed at the center. Positive charge means no electrons. Minus charge means 2 electrons. This is undistributed conjugation. This is the neutral solution which has a free radical, a positive soliton where we have positive charge, negative soliton where we have the pair of electrons. This we call it as a carbon ion, a carbocation, free radicals. This is the neutral moiety. Then the mechanism is given. A positive polar ion where we have a positive charge over the chain. It is a radical cation. Negative polar ion means where we have a one pair of electrons as in the form of radical anion. Positive dipolar means bipolar ion means there are two positive charge present in one polymer in the same chain. This materials are called as carbo dication. Negative bipolar ions means we have a negative charge over the carbon and also one radical species. It is called as carbo dianion. Few more examples of conducting polymers. Polythiophene. This unit is called as thiophene. So polypyrrole. So this one unit is pyrrole. This is pyrrole. So here at ortho position there is a substitution takes place. Polyaniline also here is a phenyl group. One change is that it has only NH group that is bonded to the phenyl position. Types of conducting polymers already we discussed about it. Doped conducting polymers. Plastics is disturbed either by removing electron from oxidation or inserting them into the reduction the material. The process is known as the doping process. Two types of doping. One is oxidation with Lewis acid, the reduction with basic catalyst. Doped conducting polymers. Plastics is disturbed either by removing electron from the oxidation or inserting them into reduction. The process is known as the doping process. Two doping process. One is oxidation with the Lewis acid. Second one is the reduction with the Lewis acid. First one is called P doping. Second one is called N doping. So the biconjugated polymers, they have an unusual charge excitations. This point is very important in the mechanism. Okay, so the conducting polymers exhibit fundamentally different charge excitations. First, there is a neutral polymer. When you add a dopant into it, like iodine or alkali metal, sulfuric acid, the double bond will make a two radical species. This double bond, one will go and bond with a dopant ion. Okay, so dopant will carry a negative charge. This terminal will carry a positive charge. Both are plus and minus. They are very close. Remaining one is as such, it is left out. And now the charge will move on both sides. Doping process. The halogen doping transforms polyacetyl into a good conductor. The symbol diagram. Oxidation with iodine causes the electrons to be jerked out of the polymer, leaving holes in the form of positive charges that can move along the chain. Doping for better molecular performance. This flowchart gives us an idea about various conductivity for various metals. Copper is at the right corner, the highest conductivity. These are all other metals. These inorganic metals, organic metals. So the conductivity of conducting polymers compared to those of other material from quartz to copper, polymers may also have a conductive corresponding to those of semiconductors. Polythiophene, the mechanism is given here. How it is forming. Thiophene is here. When you add electron into it, we end up with, it is a oxidation. This carries a positive charge. Put another sulfur that will bond at this second position, and by this electrochemical way, thiophene to polythiophene preparation. Mechanism is given here. So acetylene, the same. Adding dopant, what is happening in the valence bond, what is happening in the conduction bond, what is happening when it oxidizes polymer, when it reduces. Formation of polaron, formation of bipolaron. Bipolaron means there are two anionic species are generating in a single chain. It is dianion, and this anion will move towards this side. This will move towards this side. Comparison. Polythiophene, polyaniline. This can be synthesized in doped form and stable in air but lower conductivity. It remains the most conducting polymer but easily oxidized in the air and sensitive to humidity. Other polymers are polypyroles and polyphenylene. The last one is P3HT, that is polyhexyl thiophene 2,5 diol. This is structure. 2,5 is the substitution. C6H3 is a alkyl chain is bonded at third position. First we take this 3-hexyl thiophene, treat with the ferric chloride. We end up with this P3HT polymer. What is P3HT? P3HT is nothing but poly 3-hexyl thiophene 2,5 diol. So hexyl is placed in the third position. Properties: they have excellent electric conductivity, electroluminescence, and non-linear optical properties. They also have a low glass transition temperature, highly crystalline for a semiconducting polymers.